Today's video is sponsored by Clean My Mac.
Today we've got a video about a subject that I really like, the subject of quantum calculus. And in particular, we're going to look at the quantum integral as well as two fundamental theorems of quantum calculus. So before we look at the quantum integral, let's recall that in a previous video we looked at the quantum derivative, which was defined as follows. So dq of f of x, the quantum derivative of f of x, is f of qx, or xq, minus f of x over xq minus x. And here we think about q mostly as a formal variable, but if you want to think about it as a number, it's between -1 and 1, or maybe it could even be a complex number inside of the unit circle. And we're in fact often interested in the case when the limit as q goes to 1, as we'll see later. Okay, so we also had this like quantum analog of the natural number n, which was defined to be 1 minus q to the n over 1 minus q, and expanded out, that's 1 plus q squared all the way up to q to the n minus 1. Notice if we let q approach 1 here, this approaches just the number n because we have 1 plus 1 plus 1 n times. Furthermore, in the previous video, we showed that the limit as q goes to 1 of the quantum derivative was the normal derivative. Okay, so now let's look at this quantum integral. So it'll be defined as follows. The quantum integral from 0 to a of f of x dqx is equal to 1 minus q times a times the sum as n goes from 0 to infinity of q to the n times f evaluated at a times q to the n. And quickly you might say, well, how do I take, for instance, the integral from a to b? But you simply take the difference. So that would be the difference in the integral from 0 to b minus the integral from 0 to a, kind of using strategies that you probably learned when you first learned about integrals. Okay, so anyway, I think in order to understand this at all, we should do some very, very basic examples. And that's exactly where we're going to start. And let's start taking the quantum integral of maybe the simplest function we can think of, just the function x. So we've got that. We've got the quantum integral of x dqx. So I guess you could just take the quantum derivative of a constant. I'll leave that to you. Okay, so this is going to be equal to, let's see, 1 minus q times a times the sum as n goes from 0 to infinity of, let's see, we've got this q to the n baked into the formula. And then we have f evaluated at a times q to the n. But f is just the identity function f of x equals x. So that's simply going to give us a times q to the n. So we're left with something like that. So now we can simplify this a little bit. This will be 1 minus q times a squared times the sum as n goes from 0 to infinity of q to the 2n. Oh, but look at this. This is exactly a geometric series. And here's the part where we either think about q as a formal variable or we think about the modulus of q being less than 1, so we can appropriately sum this geometric series. So let's recall that the sum of a geometric series is the first term over 1 minus the common ratio. So let's see, we have this 1 minus q out front, this a squared, and then times 1, because that's the first term, over 1 minus the common ratio, so that'll be 1 minus q squared. But that simplifies pretty easily. This 1 minus q squared will cancel with this 1 minus q, leaving us with 1 over 1 plus q times a squared. But let's notice that that is 1 over the q analog of the number 2 times a squared. So let's quickly compare that to what we would get for the normal integral and make sure that everything is kind of making sense here. So the integral from 0 to a of x dx, well, that's clearly equal to a squared to a squared over 2 using the fundamental theorem of calculus. And now check it out. As we let q approach 1, these two start to coincide. So I think that's pretty interesting. So maybe as a follow-up exercise so that you guys have a feel for what's going on, you could show the following by hand, and that is the integral from 0 to a of x squared dqx is in fact equal to a cubed over 1 plus q squared. In other words, it's equal to a cubed over the q analog of the number 3, which when q approaches 1, that coincides with exactly what we want it to. In fact, it's a cubed over 3. Okay, so I think this is all getting us to think about the power rule for maybe the quantum integral, and now let's prove that carefully.
I want to take a few minutes to talk about today's sponsor, Clean My Mac X. I started using this program a couple of years ago when my computer started slowing down. I was trying to export videos for YouTube and was frustrated that it was taking so long. This program has really worked to declutter my Mac and free up memory so that it works smoothly. They help clean up all my clutter. I'm too busy working on new, exciting mathematics problems to organize my computer myself. Clean My Mac is easy to use and includes lots of really great features. It can help optimize your speed as well as sorting through old files so that you can delete ones that you don't need anymore. It even helps protect you from malware. Clean My Mac X will handle all of the mess after your creative process. Try Clean My Mac X with a 7-day free trial and a 20% discount for 2 weeks by using my link in the description and pinned comment. And thanks once again to Clean My Mac for sponsoring today's video.
So now let's look at this power rule. So we'll show that for all natural numbers m, the quantum integral from 0 to a of x to the m is a to the m plus 1 over the q analog of m plus 1. So let's get to it. This is a fairly straightforward calculation if you're just not intimidated by all of the notation. Okay, so this quantum integral always has this 1 minus q times a part, and then we'll have the sum as n goes from 0 to infinity of this q to the n. That's always part of the quantum integral. And now we've got f evaluated at a times q to the n. But f in this case is just the nth power function. So that'll give us a to the m, q to the mn. And now let's start simplifying. So we can bring out a to the m, leaving us with 1 minus q times a to the m plus 1. And then we'll have the sum. N goes from 0 to infinity. I'll write this as q to the m plus 1, all raised to the n power. So that'll be what's left over after we bring that a to the m out. But now all of the stuff that I'm putting this orange overline here is exactly a geometric series. And it's a geometric series where the starting term is 1, the n equals 0 term, and the common ratio is q to the m plus 1. So using our rule for summation of a geometric series, we'll be left with 1 minus q over 1 minus q to the m plus 1 times a to the m plus 1. But now, in fact, we're done. And that's because this stuff that I've got this purple underline is exactly the reciprocal of one of these q analogs of natural numbers. In this case, it's the natural number m plus 1. So we have 1 over m plus 1q times a to the m plus 1, but that's exactly what we wanted to show. Okay, so now from here, we'll show that the limit as q goes to 1 of this quantum integral is in fact the normal integral. So now we'll look at this result involving the quantum derivative and the normal derivative, and we'll prove the corresponding result involving the quantum integral and the normal integral. So let's get to it. We'll show that the limit as q goes to 1 from below of the integral from 0 to a of f of x dqx is just the normal integral from 0 to a of f of x. Okay, so here I'm just going to maybe go through with the calculation. So let's first write down the definition of our quantum integral. So we'll have 1 minus q times a, and then we'll have the sum as n goes from 0 up to infinity of q to the n times f evaluated at a times q to the n. Okay, so that's looking pretty good. And now from here what we'll do is change that infinite sum to a limit of a finite sum. And I'm going to combine that with the step of exchanging the order of limits, which is a bit sketchy for sure. But let's recall that all of this is done usually in the combinatorial setting where we don't worry about convergence. Okay, so I'll take my limit as capital N goes to infinity of the limit as q goes to 1 from below of 1 minus q to the a times, now I've got the sum as n goes from 0 to capital N minus 1. We'll see why we want to stop at capital N minus 1 of q to the n f of a times q to the n. So that's what we've got so far. But now I'm gonna look over here and think about what role these terms are playing inside of the quantum integral versus inside of the limit of a Riemann sum. And in my mind, this a times q to the n is really playing the role of x sub n. Maybe not exactly x sub n, but something similar to x sub n. So I'll put quotes around it because this isn't exactly what we'll get here. And then everything left over, so this 1 minus q times q to the n times a is playing the role of delta x. Okay, nice. So if I can make some sort of change of variables to my inner limit to make that happen, then we'll perhaps be good to go. And that's exactly what we'll do here. So let's make the following change of variables. So let's just recall that this over here was inspiration. So I'll just put a star there to say that that is inspiration. And then this purple box over here is exactly the substitution that we want to make. So we'll take a times q to the n and we'll set it equal to capital N minus lowercase n over capital N times a. So notice that this is flipped around, but I think that makes sense because let's recall that q is generally thought of as being less than 1. So the n equals 0 term will give us f evaluated at a, whereas as n approaches infinity, that q is going to be going towards 0. So this is actually stepping back inside the sum from x equals a down to x equals 0 instead of forward like would happen with the Riemann sum. Okay, so anyway, so that's something like this. So now I'm going to in fact write this as x sub n minus n. So that's when I said it's not exactly that over there. And then furthermore, we can make the following calculation. So a times q to the n minus a times q to the n plus 1 will simplify to a over capital N. And we want to think of this as delta x. Okay, so now let's see how we can rewrite this. Oh, well, actually, before we rewrite it, let's notice as the limit as n goes to infinity of this substitution, this a times q to the n, looking at it as this right-hand side, that's equal to a. But that corresponds to the limit as q goes to 1. So this is actually smashing these two limits together. Okay, so anyway, let's start writing things down. So this is going to be the limit as n goes to infinity of, now we'll have the sum as little n goes from 0 to n minus 1 still of f evaluated at x sub n minus n. And then let's see everything else that's left over. So we've got all of this right here times this q to the n. But that's exactly this term right here, which is our delta x. So I'll put all of those together into our delta x. And then just to drive it home, I'm going to do another change of index here to make it look exactly like the limit of a Riemann sum. And in fact, here I'll take little n and replace it with little n minus n. So like I said, that's just a change of index. So now I'll have the limit as capital N goes to infinity of the sum as little n goes from 1 to capital N of f of x sub n times delta x. Oh, but let's notice that that will exactly be the integral from 0 to a of f of x dx, because that's exactly kind of the limit definition of the integral. You know, given our setup, which you can of course check, that x sub 0 is equal to 0, whereas x sub n is equal to a, which is, you know, needed to tie it all together. Okay, so there we have it. The limit of the quantum integral is in fact the normal integral. Okay, so next up, let's look at some fundamental theorems of quantum calculus. Now for the fundamental theorem of quantum calculus part 1. And that'll be that the quantum integral of the quantum derivative from 0 to a is simply that function being evaluated at the two endpoints. So this is a nice result. Okay, so let's get to it. So here we've got the quantum integral of the quantum derivative. Let's write the quantum derivative here. So this is f of xq minus f of x over xq minus x. Then we have dqx here. Sorry, that should be dqx in both of those cases. So now what we need to do is apply the quantum integral formula to this function that I have underlined in purple. So we need to be careful about that, but I think that's not too bad. So that'll give us 1 minus q times a, and then we'll have the sum as n goes from 0 to infinity of q to the n. So all of that comes along regardless of what the function is. But now the function is that thing which is underlined in purple, that derivative. Okay, so let's see what we'll have here. Here we'll have f evaluated at, we need to replace x with a times q to the n, so that'll be a times q to the n plus 1 minus a times q to the n, because that's just a simple x. And now, again, in the denominator, we need to replace x with a times q to the n. That'll leave us a times q to the n plus 1 minus a times q to the n. Okay, great. But now let's see what simplification can occur. And, you know, quite a bit of simplification can occur. Let's take this denominator over here and see what we can do with it. So first of all, we can factor an a out, and that'll leave us with q to the n plus 1 minus q to the n. And then we can factor a q to the n out. So let's do that. Factor a q to the n out, and we're left with q minus 1. But now let's factor a minus 1 out, and we're left with 1 minus q. And now let's see how this cancels. So let's notice that this q to the n term here will cancel this q to the n term here, keeping in mind that we're thinking about making this yellow box replacement. And then next up, this 1 minus q term will cancel this 1 minus q term. And finally, this a term will cancel, let's see, this a term right here. And then let's take this minus and have it change these two signs here. Okay, so I think that's looking pretty good. And then from there, we'll write this as a limit of partial sums. So we've got the limit as n goes to infinity of the sum as n goes from 0 up to capital N of, well, the one attached to a plus, so that's f of a times q to the n. And then minus the sum as little n goes from 0 to capital N of the one attached to a minus, so that's a times q to the n plus 1. But now check it out. These two sums have almost all of the same terms. This first sum has an n equals 0 term that is different than the n equals 0 term in the second sum. And in fact, it's pretty easy to check that the n equals 0 term in this first sum is equal to f evaluated at a. Whereas notice the n equals 0 term in the second sum is f evaluated at a times q, which is the n equals 1 term in the first sum. And then let's look at the second sum. So the n equals capital N term in the second sum, or maybe we should like take that and put it over here. The n equals capital N term in the second term is not exhibited in the first sum. And that would be equal to, let's see, f evaluated at a times q to the n plus 1. Oh, but I almost forgot, this is all attached to a limit as capital N goes to infinity. So as capital N goes to infinity, well, f of a just stays as the constant f of a, but let's recall that we're generally thinking about q being inside the unit circle. In other words, its modulus is less than 1, or its absolute value is less than 1. So if you take the limit as its power goes to infinity, that will just go to 0. So that leaves us with f of 0, but that's exactly what we wanted. Okay, so now let's look at the FTQC number 2. Okay, so the fundamental theorem of calculus part 2 exchanges the order of integration and differentiation. And so it defines a function in terms of an integral, in this case a quantum integral, and takes the quantum derivative of that. Okay, so let's just churn through this. We'll perhaps skip a couple simple steps, but it'll be a nice homework exercise. So we've got dq of, now the quantum integral here will be 1 minus q times x. Notice the roles are switched here a little bit. The role of x here is being played by t. The role of a here is being played by x. And then we'll have next the sum as n goes from 0 to infinity, q to the n, f evaluated at x times q to the n. So we're left with something like that. And now let's apply this quantum derivative. So that means, well, we need to do this kind of thing right here. Okay, so let's maybe write this 1 over xq minus x out in front of the whole thing, and then we'll rewrite this, replacing x with qx, and then subtracting just as is. So we'll have 1 minus q times xq, and then the sum as n goes from 0 to infinity of let's see, q to the n times f of x times q to the n plus 1. Okay, so that's like this term right here. And then from that, we need to subtract 1 minus q, and then x, and then the integral as n goes, and then the sum as n goes from 0 to infinity of q to the n, fx q to the n. Okay, sick. Okay, so now let's see what sort of simplification can be done. Notice that this xq minus x, well, that's almost exactly the same as this. It's just going to change the order of the subtraction because this is like a q minus 1 and this is a 1 minus q. So this term will cancel those two terms as well as those two terms and then change the order of subtraction. Okay, and then we'll be left with something like this. So we'll have the sum as n goes from 0 up to infinity of that second term, so that's q to the n, f of x times q to the n, minus the sum as n goes from 0 to infinity of q to the n plus 1 times f of x times q to the n plus 1. But now we've got sort of the same thing as we had before. We can bring out the 0th term here, and notice that everything after the 0th term in this first sum will be canceled by that second sum. So all we'll be left with is the 0th term in this first sum, which is clearly equal to f of x. But look, that exhibits exactly the sort of relationship that we would want. So notice that the quantum derivative of this function defined in terms of the quantum integral, well, the derivative and the integrals cancel. So that's a nice result. So thanks for sticking around so long. If you're still around and you haven't subscribed, consider subscribing. It would really help the channel out. We've got some secret subscription goals that I won't release to the public right now, but I'd really like to meet them. And that's a good place to stop.